In our last video, we talked about ANOVA tests, analysis of variance, where we could see if there are differences among groups when we had quantitative outcomes. Today we're going to talk about chi-square tests, and these are used when we have categorical data, and again, more than two groups. If we just have two different groups or one groups, we can use the proportion stats and do our tests the way we've learned previously. But when we have more than two groups, that's not going to work. The data that I have set up for you here is actually taken from page 565 in your book. And it relates to a brand preference survey that the marketing department for a particular product engaged in. They took 150 consumers and asked them, with respect to a particular product, which did they prefer? Brand A, brand B, or the store brand? And we want to see if there is a difference, if there really is a preference, or if it just is kind of spread across the board. Now, it certainly looks from our data here that there is some kind of brand loyalty or brand preference. 61 of our 150 consumers preferred brand A, 53 preferred brand D, and 36 preferred the generic store brand. But the question is that enough of a difference to hold true for the population? We're trying to make an inference about the population based on our sample here. When we're comparing a single outcome variable using a chi-square test, it's something called a goodness of fit test. So we'll go to stat, and there's an option down here for the goodness of fit test, and chi-square. It looks like chai or chi or shy, but it's pronounced chi. We go to our chi-square test. Our observed values, one of the things that the chi-square test does is it compares the observed values from a sample to what would be expected under certain circumstances or given circumstances. Our observations here are in the consumers column, and our expectations would be that all of them would be equal. We want to see if there's a difference, if there's any kind of brand preference at all, so our expectations are that they were equal, because if there's no preference, we'd expect 50 in each cell. That's all we have to do. We hit compute, and we get our results. We have a chi-square value of 6.52. We have a p-value of 0.0384. Just like all the other tests that we've done, if that p-value is less than 0.05, that's telling us this is a significant result. We can reject the null. There is a brand preference there. They're not all equal. There's a distinct consumer preference. And here it actually lays out what the observed results from our sample were compared with what would have been expected if there was no preference. One other thing to mention, the total number here is 150. They also show us our degrees of freedom, or DF, and for a chi-square test, degrees of freedom are the number of different groups, those who prefer brand A, brand B, and generic, minus 1. So that's where the 2 degrees of freedom come from. It's our 3 groups minus 1. I want to take a look at a couple of other situations here with chi-square tests. For this next one, I'm going to call up this file called loads. This data is actually based on problem 10.17 on page 571. And this data came from the state of Minnesota and their highway department. And they were trying to find out if truckers were more likely to run the scales when they were overweight on certain days of the week. So they took the number of overweight vehicles because they installed a surreptitious weighing device in the road so they could tell how many trucks passed over that were overweight, so they took that number, and then they looked at the total volume of traffic that was on the highways on those different days. And it would make sense that the proportion of overweight trucks should be about the same as the proportion of the total traffic. And if there's a difference in the proportion of overweight trucks compared with the total proportion of traffic, then they must be specifically targeting one or more of those days. And if that's the case, we can put in extra, make sure to have the weight scales open on those days to try to detect that. This is a situation where we're not going to have just completely equal expectations. Our expected results would correspond with the volume proportions here. So we'll go to stat, goodness of fit, chi-square. Our observations are going to be in the number column. And for our expectations, instead of setting everything equal, we're going to choose the volume column. We're going to see how well the number stacks up with the volume. We click compute. We get a p-value of 0.0541, which is just slightly more than 0.05. We don't have quite enough evidence to show that they would appear to be targeting particular days. But we can also see what was observed on the different days of the week. Monday we observed 90. We would have expected only 79. So it does look like there may be something going on that they're more likely to try to be overweight on Monday. Also Sundays, we observed 31. We would have expected only 19. Other days, such as Saturdays and Tuesdays, you can see we ended up almost right on what would have been expected there. So this tells us a couple of different days that we might look for. Again, our p-value here was slightly over 0.05. So technically, from a research standpoint, we would have to say there's not enough evidence to come to a conclusion there. But if we were the state, we might want to go ahead and make some additional staffing on Sundays and Mondays anyway. Our last chi-square test that I want to look at is discussed on page 572, and that is a two-way contingency table. What if we had two different categorical variables that we're interested in looking for a relationship between? Table 10.3 on page 572 shows us data from, again, a marketing experiment. Marketers often use chi-square tests. It's in the data file called CELEB, C-L-E-E-B, here in chapter 10. And unfortunately, kind of like we had to do with the factorial ANOVA data, we're going to have to make some modifications here to this one as well. We want our data to look like table 10.3 on page 572. So we're going to make a column here called aware. We're going to make a column called male, and we're going to make a column called female. We've got identify, and what they did, they showed ads with different celebrities in them, and then they showed them to males and females, and they asked if they could identify the actual product that was being sold. And 95 of the males that they asked were able to identify the product, 41 of the females were able to. And for not being able to identify the product, 50 males could not, 114 females could not. So it appears that there is some interaction here between gender and whether or not they were able to identify the product. What we want to do is a statistical test to see if that bears itself out. We're dealing with categorical data, male or female, ID the product or not ID the product. And we have more than 2 groups. We've got 4 different cells here of information. We'll go to stat. This is a contingency table. So we want tables, contingency, and we want summary. We don't have the raw data of what each individual said. We just have the summary of that data. The columns that we're interested in are male and female. And the row labels are in the aware column. We click compute. We get a result here that does in fact look very much like table 10.2 in our book. It shows how many fell into each of our different cells, the total for each row, the total for each column, and then it gives us our chi-square test. And this chi-square test shows us that the p-value is less than 0.0001. There is a significant difference here. There is an interaction between gender and the ability to identify the product that was being advertised by those celebrities.